Okay. All right, first thing we're going to do is a little bit of housekeeping. So, hey man, stuff happens. You adapt, you improvise, you overcome, and you accommodate. So, I told you guys on Wednesday that the little workbooks, the textbook, I don't work with the bookstore on that because I don't, none of that comes back to me. That's the department that works with the bookstore. I'm sorry, man, class started. In fact, I thought I checked the door to make sure it's locked. So, is that door cursed? Let's see. All right, next time I'll get the belt door. So, department, bookstore, miscommunication, books, blah. So, all we can do is accommodate. So, usually I don't have the slides up on the screen. Usually I have a chalkboard and I misspell a bunch of words and we roll on, but I'm going to put up the stuff that I'm going to talk about so that you guys can take out your phones and snap pictures of anything you need. And so I'm going to accommodate you guys. And then again, this is the first time ever doing this. I'm going to post all the lectures on Google so that way you can clarify and make sure everything's answered, okay? That's all we can do. I left my potter wand at home, so we're going to do the best that we can. So that being said, let's talk about motion. And motion, and listen, just a preference, okay? I'm not going to give you like 10 walls of it. I'm not going to overwhelm you with stuff. I'm just going to tell stories and try to actually make this real simple. Human movement can be complicated, but it's made of simple principles. Think about it like this. Great chefs that put together these amazing dishes, they have talent to do that, but it's made of simple ingredients, right? They just know how to play with it. So all the concepts I'm going to teach you are very basic concepts. It's the application that kind of takes a little practice and getting used to, okay? So the first thing I want to kind of talk to you about is motion. And when you think about something, or you ask yourself the question, is it moving? It's a very open-ended question. Is it moving? What I'm going to try to teach you guys is that is it moving can really be broken down into two types of movement, right? Is it moving? And the two types of movement is straight line motion, up, down, left, right, front, back, and then rotational motion. And we're going to talk about how rotational motion can spin. Similar concepts to up, down, left, right, front, back, but we got to give it names. So another way to look at this is, am I moving? Yes. Am I going anywhere? Yes. I'm going to the left of class, as you see it. But what about a merry-go-round? Is a merry-go-round, when it's spinning, is it moving? Yes. But is it going anywhere? No. The merry-go-round stays where it's at. So you don't have to be going anywhere to move. But obviously there's a difference when you're moving and going somewhere than when you're just moving and you're not going anywhere, okay? And that's kind of the layman's terms example of rotational motion. Pure rotation is a concept we use to describe something that's spinning but it's not going anywhere. And translation is a term we use to describe pure straight line motion where something's going somewhere, but it's not spinning. And then the dreaded combination. You can have a combination of both. In fact, most motion is a combination of both. It is hard, really, really hard to have pure anything. What I mean by that is if someone was doing a vertical jump test, right? Jump as high as you can. And we know that that's a test where you're trying to go straight up. but the odds of them landing a little bit further than when they jumped, or a little bit behind. In other words, any little bit means they didn't go entirely straight up. Think of it directionally. You have north, south, east, west, but it's almost impossible to go purely north. I mean, a little bit of variation means some of that is east, or some of that is west, or some of that's south, some of that's east. That's why we have northeast, northwest, southeast, southwest. So it's the same concept, that even though we kind of have these 8-set Crayola concepts, life is made up of different shades of all those types of basic colors. It's true. I learned that the hard way, man. Growing up, I was like red, green, what else is there? Fuchsia? God, they don't, man. There's a lot of different shades. So in my simple brain, red is red. But my wife is very quick to say, no, Brian, that's apple red or something. I don't know. So the blending of motion, although it can be complicated, it's actually made up of straight line stuff, rotational stuff, and the mixing of them together. And my job is going to teach you how to extract what is up, down, left, right, front, back. But more importantly, my job is to teach you about the spin, the rotations, because that's how our bodies move. This is what I mean by that. An elevator takes us up and down. That's great. But there are things rotating. There's cogs and wheels and things. Because something has to stay still. Something has to stay still. For us, if I were to make my whole body go up and down, right, without rotating anything, I would have to be a wizard or a Jedi. Right? In other words, think about it. Go up. I have to spin something. I have to rotate something. Remember the movie, I always loved pop culture. Remember the movie Baymax? What was it, Big Hero 6? In cartoon fans like that. So Big Hero 6, Baymax could shoot his hand out, right, forward. That was motion that he could do with his little rocket hand. We can't do that, man. If we had segments that straight line move from us, it's called a dislocation. We would have bones pull apart from bones. The only way for the bones not to pull away from bones, but yet us have movement, is to have rotations. It's similar, not exactly a better analogy of the merry-go-round, where the merry-go-round is moving but it's not going anywhere, is like when you do this to your head. The merry-go-round is moving but it's not going anywhere. But we have a lot of different ways we can move, but not necessarily go anywhere. So the key thing for human motion is rotation. We rotate in order to translate. We spin things in order to get us places. And get us places could be your whole body, but it could also be your hand, if you need to get your hand in a certain place for a throw or a catch. To get your foot in a certain place for a kick or a block. We rotate to translate. We spin things in order to get us certain places or do certain things. Okay? So, some examples of, now keep in mind, guys, I'm going to go in this in more in depth. I'm just introducing you to these concepts, and then we're going to develop them, and then we're going to master them. I will say, a lot of times these concepts aren't easy to ingest because your familiarity with motion is typically up, down, left, right, front, back. Straight line stuff. North, south, east, west, up, down. And for us, kind of the more important thing is the spins, the rotations, and that's just a little different. Similar concepts, but it's just a little different. Okay? So the basketball can go down and up, left, right, front, back. But how can the basketball spin? Okay? The basketball can spin. If the basketball can move in 3 different dimensions, when you put on 3D glasses to go watch a 3D movie, what are the 3 dimensions? I can see the movie up, down. I can see the movie left, right. Whoa, the movie's coming out at me, right? It's the 3rd dimension. So the basketball can move in the up, down, like the movie screen. It can move to the left, right. Whoa, it can come at me. And anything that you might perceive as a different dimension is actually just a combination of those 3 blending into new colors, a spectrum of motion colors. I can go forward, up, and across. I can go down and to the left. So there's no infinite dimensions. There's infinitely many combinations of the main 3 dimensions. And then when they get smart, they're like, in 4D, we're going to add senses up, down, left, right, front, back. That's the easy part. The harder part is to say, well, if we have 3 dimensions of straight line motion, which, you should be pretty comfortable with, it should be logical to say, well, then there should be 3 dimensions of rotational motion. There should be 3 dimensions of spin. There should be 3 ways this ball can rotate. Okay? I'm not going to use a basketball to explain the 3 types of rotation. I'm going to use a young gymnast. My sons, when they were young, they used to go to the little gym to get out some energy, and it was real cool. And my sons had little flexibility like their dad. And when they were at the little gym, or did any of you work with kids, with young kids, and tumbling, anything like that? So let's think about 3 ways you can get a child to spin. Now, the basketball and the child obviously different, but they're actually kind of similar. They're both objects made of stuff, and they both have a concept called a center of mass, which is basically just the average distribution of the stuff they have. Okay? The average amount of stuff, up, down, left, right, front, back, is usually in the middle of the object. But if you have more stuff higher or lower, it could be a little higher, a little lower. Men typically have a little higher center of mass than women. Women typically have a little lower. But if you ask a child to rotate or to spin, think about the 3 ways they could do it. Like maybe a front roll or a back roll, right? That's a certain type of spin in a certain dimension of spin. What else can the kid do to spin? Maybe a cartwheel, right? To the right, to the left. And think of the similarities. Basketball, translated forward and translated back. That's 1 dimension. Interstate 10 is 1 road. It can go 2 different ways, but it's 1 road. Forward and back are 2 different directions of motion, but it's 1 dimension. Does that make sense? Okay. So how can the child spin in this plane, this dimension of rotation? The child can roll forward or roll back. It's the same road, just 2 different directions. I could take, or I'm live, I ain't going to use a basketball, but I could take the basketball and I could spin it this way or that. I need help. You catch it? Anybody catch it? Ready? So watch, I can spin it like this, spin it like that. Exact opposite, right? But it was in the same rotational dimension. I would show you guys what a backflip and a front flip would look like. However, I'm going to be giving that up for Lent, and I'm just, getting, I just need to segue into not doing those kind of motions. So, a cartwheel to the right or to the left, how would a basketball spin? This, or like this. It's a dimension of rotation. And then finally, the 3rd dimension of rotation. And listen, we're going to give them names and all that stuff. I'm just trying to get you to see how rotation kind of has its own set of rules that are similar to straight line motion. How else can we get a child to rotate? Hey kid, you want to get dizzy? Spin to your right. Kid starts doing this, right? All right, spin to your left. That's a third dimension of rotation. Basketball players do something like that, right? Where they spin like a kid would spin. That's a dimension of rotation. The merry-go-round spins in a dimension of rotation. The tire spins in a dimension of rotation. Okay? Now, planting the seeds of translation and rotation, straight line motion, the rotational motion. Came up with these Kinesiomandments. Like what I did there, huh? This is in conjunction with other students when I got feedback from class, and I was like, guys, what do you think the next generation of students need to know? Or what do you think they're most likely to get tricked on? Some people say my class is tricky. It can be if you don't understand what we're talking about. I could go to a German class, and that's very tricky to me because I don't speak German. But if I speak German, then it won't be tricky. Here's the key. Imagine you're a medical doctor, a surgeon. You've been working long hours, you're tired, you're 24-hour shift, and there's an emergency, and you have to amputate the right arm as soon as possible. Amputate right arm ASAP. You go into the ER and you amputate the right arm, and then you realize, oh, his right arm. That's happened. Who's right? My right? Their right now, because that's happened. Guys, you ever saw that? These are usually on Facebook and memes, but there'll be like Superman costumes for Halloween, and it'll have like a little warning tag. Wearer of this costume will not be able to fly. And people laugh at it, but that means someone had a kid who thought they were they could fly. Surgeons now and their prep teams and their nurses put big red X's on the limbs they're not supposed to cut on. Why do you think that is? Because who's right? My right? Their right? Perspective. Okay? So a lot of what we're going to be talking about is not just perspective, but the temptation to want to go one way because that's what you're comfortable with in straight line world. And I'm here to say, whoa, before you go there, think about it. Because rotational world doesn't necessarily link up with straight line world. It's a different universe. It's like DC and Marvel, man. It's a different universe. It's not to say they don't have similarities. There's a lot of similarities. But spinning to your right or spinning to your left doesn't necessarily link up with moving to your right or sliding to your left. Okay? So we have some when I got with some of my former students, these are some of the, hey, if your future students could learn these, they will be less likely to make an oops, less likely to make a mistake, more likely to make their 3-foot putts. Okay? We rotate to translate. I kind of mentioned it earlier, right? We spin certain things in order to make other things go forward, go back, left, right, front, back. Okay? Joints rotate in planes and joints rotate about axes. That's important as well. I'm going to lecture on it next week, but just I'm planting seeds of importance. We analyze motion joint by joint. To me, that's one of the best ones because what it does is it absolves you from being overwhelmed with motion analysis. Guys, we're all going to be biomechanics because we're all going to be working with people, and people move. Motion is life. When you stop moving, and I'm not just talking about macromechanically, I'm talking about micromechanically, parts and vessels. When you stop moving, you no longer live. Motion is life. So we will be working with people who move. So we have to make sure we understand that whoever we're working with, it's from their perspective of motion, not ours. Okay? We analyze motion joint by joint. Guys, sometimes these movement strategies can be totally overwhelming. Anybody remember The Matrix? No, it's an old movie with John Wick, right? He's doing, whoa, he's dodging bullets. That's a crazy motion. However, any motion you see is actually just the sum of very simple parts. Put it this way. I look at a car and I say, that's way over my head. But a mechanic looks at a car and says, oh, it's actually very simple. I mean, together it's a lot of stuff, but it's just made up of this little part does this, and that little part does this, and this little part does that. So a motion might look complex, but the reality is it's made up of simple parts. The ankle can only do so many things, and the knee can only do so many things, and the hip can only do so many things, and the trunk can only do so many things. So I'm going to teach you how to analyze complex movement by breaking it down. Analyze motion, joint by joint by joint. It's going to be simple. It'll be a lot easier too. Oh man, do not assume. Let me give you some examples of these. Do not assume motion has occurred. What's an example of that? If I say, hey, what's my shoulder doing? And I do this. It looks like my arm is moving, but so is the socket. So when we talk about motion, it's going to be very specific. Don't assume, just because something looks like it's moving doesn't mean it's spinning. That's what I'm trying to get to. Just like the basketball. Is the basketball moving? Yes. Is it spinning? No. Or something may be spinning, but not between the hand and the basketball. What I mean by that is, if I said, is there motion at my radial ulnar joint to spin the basketball? Yes. Is there motion about my radial? So in other words, the rotation there was in my hips as I walk around. So just because the ball is doing this doesn't necessarily mean it means it's at a particular segment. Here's another example. Let's say someone was in a halo, which is, they put that on your neck to prevent you from, you've got an injury or something. So just because someone has an apparatus to prevent neck motion doesn't mean they can't look to the left or look to the right. But just because they look to the left or look to the right doesn't mean they move their neck. That's the take-home point here. You can't analyze human motion by saying, if you look to the left, it must be this. And if you look to the right, it must be that. We can't do that. Sometimes it's going to get us into trouble because we assume motion has occurred because of. I'll give you another quick example. Just because my arm goes up doesn't mean I had an abduction. And just because my arm went down doesn't mean I had abduction. See the difference? So you just can't assume. If I was in a cast, right? I can still make my arm go up and down. That doesn't mean I can move my shoulder joint. That's what I'm trying to get to. Okay? Do not assume motion has not occurred. Ooh. Here's an example of this. Again, look to the left, it must be. Look to the right, it must be. If I keep my eyes fixed on something. Let me go back. How many of you have been introduced to joint motions, maybe at 100 level classrooms? And listen, I'm not here to say they're wrong. That's not what I'm hearing. They're right. However, they haven't given you, we haven't gone down the rabbit hole. It was an introduction, which is great. One of the reasons this is more difficult is because it's the difference between regular engineers and biomechanists like myself. What I mean by that is engineers, I said this on Wednesday, that door will always move like this, and that door will always open and close accordingly. There's never exceptions. So when you're introduced to these terms, the introduction is like engineering. Look to the left, it's called this. Look to the right, it's called that. When the door does this, the door does that. The problem is that in biomechanics, that door can stay put. Watch. Open, close, open, close. In biomechanics, I don't have to just move this bone about that one. Sometimes I can do this. This is open. That is open. But they're rotating in two different directions. So what I'm trying to get to is that it's not that they're wrong. It's just that there's a little more to the story. Snow White and the Seven Dwarfs can be a 10-page children's book or a 3-hour epic movie, depending on how far you want to go down the rabbit hole of the story. So here's an example. A lot of your introductory joint motions was this. What I'm trying to teach you is that this is the same as that. I go from looking at my sternum to looking at my left shoulder, yeah? What shoulder am I looking at? How'd that happen? Because I looked to the left. You're taught things like abduction. I'm not saying that's wrong. I'm just saying there's other ways you can abduct that doesn't look like that. And in lies the illusions. Because even though it looks like my leg went out, it actually stayed in its anatomical position. In other words, if I had a cast on my left leg and I couldn't move it if I tried, I could still do this with it. So where was that motion? My right hip. So I'm prefacing, I'm planting seeds that there's more to the story. That's all. There's more to the story. Okay? Here's another example of illusions. I get into illusions a lot. Right hip, external rotation. Internal, external, internal, external. You've probably been introduced to that. And I'm not saying they're wrong, they're right. What I'm here to tell you is that external and internal hip rotation can also look like this. And from here to there is the same motion as from here to there. And that can mess with people's minds. But if we understand why it can mess with your mind, then maybe we could better understand how to get it to not mess with your mind. So I'll give you an example. Lefty loosey, righty tighty, right? But that's only from a perspective. I look down and I say lefty loosey means that this bottle is going to open. But I don't have to open this bottle with the cap. Cap spins like this, the bottle's going to open, I get to drink. Guess what? If I take the bottle and spin it to the right, what's going to happen? It's still going to open eventually. It's perspective. That this to this is the same as that to that. Oh, I'm sorry, this to this is the same as that to that. Cap spins like this gives me the same motion as bottle spinning like that. That's what I'm trying to get to. The problem is that when you're only introduced to one of the segments, your body wants to hold on to any time something spins like this, it has to be that, and that's not the case. One of the biggest misses in class is hip motion. And the reason is, just like what I did with the cap in the bottle, is that you're so used to saying external, internal, external, internal. If I see anything on this right side doing that, I'm salivating external rotation. Ring the bell, good. And what I'm trying to get you to see is, don't look at it like that. Look at it as, where did I start, where did I finish? Another way to look at this. If you're in a car and you go to sleep, how many of you like to sleep when you drive long distances? Okay? All right, all three of you. You fall asleep. Maybe you fall asleep before you even hit the interstate. day. You have no clue how you travel. Maybe you didn't even know where you were going. Go and eat someplace. It's a surprise. You wake up and you're in Lake Charles. How did you have to travel to get there? You had to go west, right? You didn't see yourself go west, but you know if I started in Lafayette and I ended in Lake Charles, I had to move west. That's how I want you to look at motion. I want you to look at motion. How did I start? How did I finish? How did I start? How did I finish? And an easy way, if that doesn't work for you, I'm going to take that adapter off and put in another adapter. If you know how you have to travel to go home, then you can infer how you had to travel to leave home. Meaning, if you're in Lake Charles and you got to go home, how are you going on the interstate? You're going east. If I go from here to there and you're like, Dr. Campbell, that makes no sense. Why in the world is that external rotation? And I'd be like, okay, we started in anatomical position, and I ended here. How would I have to rotate my hip to go home? Wouldn't I have to internally rotate it to go home? So I had to externally rotate it to go out, to leave. Techniques like that I'm going to teach you and encourage you and say, look, there's no tricks with this. If you can see where a joint position is, and then you can see where a joint position is at, then you can infer how it had to move there. Left, looking to the left. We're going to get into what that's called. But I spun to the left. Looking at my left shoulder. How would I have to move to go home? I have to spin to the right. I also spun to the left. How would I have to move to go home? I have to spin to the right. Now, you may say, well, that doesn't seem fair. It seems like you're playing on verbiage. I saw your body spin to the right. How is that to the left? And it's the same reason with lefty-loosey and righty-tighty. In other words, you had to get a perspective. The whole concept of lefty-loosey, righty-tighty is that a smaller thing is moving about a bigger thing. And you think about the faucet, right? The smaller faucet is moving about the bigger house. So it's very similar. If my head is the faucet moving about the house, I'm going to see left and right from the perspective of the smaller thing. But in biomechanics, I can actually move the house. I can actually move the house about the faucet. You think of it as a dollhouse if you want. So that's why things may not seem what they are. Because your instinct is to say, I spun to the right. But the reality is, you spun to the left. Your neck spun to the left. Okay? So we do not assume. Don't assume, don't assume, don't assume. Now, that being said, just because we don't assume doesn't mean we can't, and this is a very important I word, infer. We can infer. What does that mean? That means you gave it some thought. That meant you looked for clues. That meant you analyzed the situation and then you came up with a conclusion. That just doesn't mean the bell rang and you was out there. That's a big difference. That's a big difference. When you assume, you just, that goes up, let's go down. When you infer, you say, okay, I know what I want to say, but let me just make sure I'm seeing it the right way. Let me make sure I'm looking for these clues that Campbell's teaching me how to do. That's what inference means. You infer. So don't assume, don't assume, don't assume. Infer, 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 infer. The next ones we're going to get into when we talk about muscles in the second half of the semester. All right. When I lecture, again, I'm a little different. We're all different. The analogy I like to give is there's two types, there's infinitely many types, but there's two main types of people who travel. My mother loves a straight up plan. We're going to leave at this time. We're going to exit here to get lunch. It is very, very planned. I am not like my mother. I like to take the country roads. And I like to stop every now and then just to check things out. Now, the point is, if at the end of the day the task is to get to Shreveport, that's the goal. It shouldn't matter the route you take as long as you get there. And I'm a country road driver. I know at the end of class today, when I come to class, I know where I want to get you. But I have no idea the route we're going to take. And that's just how I teach, okay? That's how I teach. So what I want to talk about today, or the last part of class, is the concept of what a plane means. I'm not talking about the airplanes, I'm talking about planes. What does that really mean? And a plane can mean something in straight line world, and it can mean something in rotational world. In straight line world, doctors and therapists and physicians, they use it for views of the body, right? So in other words, a lateral view is like a plane, and an AP lateral view. So in straight line world, you're probably used to seeing like a transverse view of something, a frontal view of something, a lateral view of something. But in straight line world, it ends there. It's just a view. It's almost like, where is the screen when you view something? Rotational world doesn't work like that. Because in rotational world, plane is associated with something else. In the medical world, when you're just looking at images of x-rays and of MRIs, there's no motion there. It's just a still picture. In fact, when you're getting these images, what do you need to do? Stay still. There's no motion at all. Planes to biomechanists, to engineers, specifically means rotation. In fact, it's a rotational dimension. That's what our 3D, 3 dimensions of rotation, things rotate in planes. That's what a plane is. It's a rotational dimension. It's a dimension of rotation. What is always associated with a plane? It's a word. It's not habitability. What's always associated with a plane? An axis, yeah. You never talk about axes when you're looking at MRIs, right? When you're looking at the AP plane and the transverse plane of MRIs, there's never axes involved. And I'm not saying there should be. There are words that can mean different things. Okay? But in biomechanics, in human movement, planes are always associated with axes. Objects rotate, all objects must rotate in a dimensional space called a plane. Now, the cool thing is that straight line motion and rotational motion have a connection. And the connection is the axis. It's just how you think about it. Like, in other words, it's like, wow, I never thought of it like that. But if you think about what an axis is, isn't it a straight line? An axis, even if it's mythical, in other words, the door rotates in a plane about an axis that's a straight line. The hinge is a straight line. So, this link between linear and rotation are our axes. And our axes can go in 3 dimensions. Forward, back, left, right, up, down. So this is where it should get kind of easy. In other words, if you say, this is what a left-right axis would look like. Straight line, left, right. But we got to give it a name. We got to call it something. To call this state something, we have to call this building something, we have to call this room something, we have to call you something. Sometimes when people are mad at me, they call me something. Straight line, left, right. Straight line, front, back. Straight line up, down. What else do we know about planes and axes? There's a P word associated with planes and axes. It's a P word. Not a perpetrator, but perpendicular. That's right, perpendicular. They're always perpendicular to each other. And so watch, this is how it works. It's like magic, man. How can the CD rotate about the pencil? There's only one way. It can't spin like this. And it can't spin like this. The only way it could spin is perpendicular. That's a dimension of rotation. And we call it something. We call it the sagittal plane of rotation. Not the sagittal plane of looking at an MRI. Not the sagittal plane of looking at an X-ray. The sagittal plane of rotation. It's a dimension of spin. It's when the kid does a front roll or a back roll. Yes, sir?
Is it always going to be that?
Oh, no. No. It will not always be that. But I'm going to teach you about that. I'm going to teach you about perspective. I'm going to teach you about local and global references. So good thought. Think of it like this. If this was a gymnast, a high bar, right? Y'all know what I mean by that? A high bar, and the gymnast rotate about the high bar? There's only one way that gymnast could rotate about that high bar, right? Like this. They can't go like this. They can sway, but they can't spin. They can't go like this. There's only one way. So now let's put the high bar like this. There's only one way that you rotate about it. There's only one way the CD can rotate about it. So straight lines serve as the point about which things rotate. That's pretty cool. This would be a frontal plane spin. If the kid was doing cartwheels, right? That would be frontal plane. Now, sometimes people spin about poles like this. I don't judge. Transverse plane. Now keep in mind, transverse plane of spin is different than a transverse plane for an MRI, an X-ray, a transverse view. What I'm specifically talking about are dimensions of spin. So, if you say, well, Dr. Campbell, how would that associate with, because I'm very confused. Look how it's a view. Yeah. But there's no motion, right? That's just a still picture. So if you want to truly understand the concepts of planes and spin, in your mind, make that dude start to spin. If he started spinning like this, that would be sagittal spin. If he started spinning like that, that'd be frontal spin. If he started spinning like this, that'd be transverse spin. You can't have motion. You can't have movement in a plane without motion. And if something is rotating, it must be rotating about a straight line somewhere. Now, that is, of course, there's going to be more to it. Great question. Does it change? Yes. The concepts don't change, but the perspective changed. Just because you asked that great question, I'm going to give you an example, but I'm going to lecture on this next week. Imagine the gymnast is, let's say the pole is in the front of class, and it's a left-right axis. And we're going to give that names next week. But the gymnast is spinning like this. You see it in your sagittal, right? But what if I'm like coaching the gymnast and I'm standing on the side? How do I see the gymnast spin? Yeah, so the gymnast may be in your sagittal, but the gymnast may be in my frontal. Both of them are okay, as long as you communicate the perspective. My father-in-law, it was colorblind, and I'm sure some of you are colorblind. Just because he couldn't pick out red doesn't mean he was wrong. You see what I'm saying? Like, that's how he perceived that color. So we're going to talk about reference systems and local references and global references. And it's going to be very important because when you're analyzing someone, you have to remember it's from their perspective. It's from their perspective. Okay? I'm going to lecture on it. Don't stress about it, just kind of looking ahead. Let's give some names to some of these straight lines while we're here, though, okay? Let's see. So, this is a little challenging because, think of it like this. Your book is sitting like this, but the screen is sitting like this. It totally changes the perspective because I can't teach you like this. So the intent of this picture is actually to be flat like this. So in other words, when you see AP axis, right? So the anterior posterior axis is a straight line from the front to the back. So you say, well, whoa, what's that? That's because the book had to do this. But if the book was like this, like some of we have, you're going to see that it goes up and down. Does that make sense? Okay. So anterior, posterior. But before we get into, let's think about how simple it is once you set reference systems. Where's the front of class? Where's the back of class? Where's the top? Where's the bottom? Where's the sides? So anterior, posterior to me, but there's also anterior, posterior to the class. Front to back. A straight line that goes front to back. Well, how does the gymnast have to spin about that straight line? Does that make sense? So an anterior-posterior straight line, or anterior-posterior axis, is going to always be associated with frontal plane spins. Even if I change it, even if I keep it in my perspective, my front to back is always going to be associated with frontal plane spins. Because if I move the axis, I move the plane. They all go together. Side to side. This one doesn't change. That's kind of cool. Side to side. Think of it like this. If anterior, posterior, front to back, well, if I had something that went one side, the other side, it'd be both sides. What's another word for both? Bi. Side is lateral, so bilateral straight line, bilateral axis. Pretty simple. And if the bar is like this, how will the gymnast have to spin? Sagittal plane. So sagittal rotations occur about bilateral axes. And even though we can perceive it different, that doesn't change. That anterior, posterior axes will always and forever have frontal plane rotations. And bilateral axes will always have sagittal. They are married, man. The divorce rate is 0%. They never come apart. Polar axes. Now, this is, Brian, what is a menu? A cat. If I say menu, and can someone say that's wrong? No, it's just what we call a cat. And they call cats other things in other languages. So my point is that it's the concept of this axis that's important. What do we call it? Some people might refer to it in other universities, other places, longitudinal axis. Big whoop, we gotta call it something, and we all have to call it the same thing. So in here, we're gonna call it polar, because to me, that's just a lot easier than longitudinal. But that doesn't mean you're wrong if you call it longitudinal. It's just that some people say menu, some people say cat, but it makes sense if I'm trying to test you on material, you're trying to study with other people, it's like, look, let's just call it cat. And there's going to be other times where you're like, well, Dr. Campbell, I was taught that's called this. That's awesome. That's a menu. It's the concept that's important and us making sure we're all calling it the same thing. Sometimes people say external. Sometimes people say lateral. It's the same thing. Lateral collateral ligament. I've heard it called fibula collateral ligament. It's the same thing. It's cat menu. The important thing is that we're not calling the same thing different things, if that makes sense. We just have to all be on the same page. All right. No class tomorrow, right? Of course no class tomorrow. No class Monday. I will upload the lectures. Do not be late. All right, have a good day.